Okay, good afternoon, class. If you haven't already done so, go into chat and sign your name so you can get your extra credit points. Okay, good afternoon, Nigel, Keston, Kendra. Let's see, there are two others on. Lanisha. Okay, and Lex. All right. Welcome, welcome, welcome to another session of physics. I hope that you all are learning something. I hope that this class is helping you to develop your math skills, your thinking skills, especially your critical thinking skills, your analytical skills, deductive reasoning. All that is what you are supposed to gain from a physics course, as well as learning the rudiments of problem solving, best practices, uh, committing equations and concepts to memory. All that is what we are supposed to be doing. So let me ask you, go into your chat and let me know, yes or no, are you benefiting from this class at all? Are you learning something, yes or no? Yes, I'm learning something. No, I'm not learning anything. Okay. Yes, thank you. Okay, Keston, yes. All right, Lanisha, great. You see, I don't want this course to just be something you are required to do just for credit, but I wanted to enhance your overall learning. In other words, the reason why you came to college is because you want to emerge a student more prepared to answer the complexities that we see in life. Even if it's not your specific job to do so, you can at least weigh in on it. So, believe it or not, being able to think clearly in physics, that skill can be used in any of your disciplines, in any of your classes. When you learn how to set up data, when you learn how to do deductive reasoning, all of that is a part of what you are learning. So when you leave this university with your degree, you are a well-rounded student. So I'm hoping that you're learning something. I know that it's a little bit boring. It's a little bit boring for me because actually when we're in the classroom and I have a little bit more time, which I don't have here, I'm able to get to know you guys, talk about current events, crack a few jokes, share candy, just talk about life in general. And unfortunately, with them having cut down our time, I really only have time just to teach. I don't even have time to get to know you the way I would in a regular classroom setting. But with that being said, I do want to say that I appreciate the response that I'm getting from you all when I ask you to do an assignment. You turn it in a timely manner. I appreciate that. When I ask questions during the lecture, you come on in private and give me your answers. I appreciate that. And also, I want you to know that my goal is for you to be successful. I want each of you to earn an A in this class. An A in a 4-hour credit hour course can really boost your GPA. And it also always looks good on your transcript to have earned an A in physics. And I know you all are capable of doing that. So our next exam is going to be on this weekend. It's going to be our midterm exam. And I'm going to be covering chapters 1 and as far as I get to Thursday with chapter 4. And then half of our lecture on Thursday, I'm going to be doing a little review. Okay, with that being said, do we have any questions about anything? Any questions in the homework? I'm going to put the homework up now, and we're going to let you grade your own papers. You should have it. You sent it to me already. And in that, we're going to see if you understand what you've done. So, with one exception, Each of the following units can be used to express mass. And of course, now we know that a Newton is not a unit of mass, it's a unit of force and or weight. So I'm going to send all of this to you. After the class, I'm going to copy and attach this to an email and send this to you. And if you have any questions about it, now this is important. I will be taking from this assignment similar questions that would be on the exam. So that would mean then, if you can solve all of these, you can solve anything that's on the exam from this 4.1. I'm going to send 4.2 after today's lecture. So I'm going to send all this to you, but I wonder, did everyone get the answer for number 10? What is here? Did everybody get that? Look at your paper. Did you choose E for number 10? Did you choose D for number 11? Because those are type questions that I'm going to be asking in the exam. That's why I'm asking that now. So you can go in chat. Let me know if I need to review any of these problems. Let me see. Okay. So Alex, Lex, should I do number 10 or 11 or 12 on my whiteboard? Okay, wants to review 10. Okay, very good. Let's review 10. All right. Okay. So we have two forces. Let me see if I can't move this down. So hold on. And get enough space. Okay. Okay, so the first thing you want to do is you want to draw your free body diagram. So this is my free body diagram. Two forces act on a 16 kilogram object. So right here is my object. And the mass is 16 kilograms. The first force has a magnitude of 68 newtons and is directed 24 degrees north of east. So that means that I have this force. I call this force 1. And this angle is 24 degrees. So that means that for force 1, I have force 1 on the x-axis and force 1 on the y-axis. That's what it means. The second force is 32 newtons. Okay, this force 1 is, let me see, force 1 is 68. Now, because we have done this so many times, we know now what to do. We know to say for F1x, we're going to say cosine of 24 times 68. We know to do that now because we've done this enough times to know what that means. So someone go ahead and calculate for me what is F1x and what is F1y. So if you don't have your calculator, run quickly and get a calculator. We're going to need it to work together in this lecture. We learn the best when we're interactive, when we're actually doing the work. So first thing you're going to say is cosine of 24. Get that number. I got 0.91. And then you're going to say times 68. So I got 62.1. So F1x is 62.1 newtons. Okay, F1y, I'm going to say sine of 24, sine of 24, and I get that number, I got 0.40, and then I'm going to say times 68, and I get 27.65, 27.7. Let's see what somebody's saying over in the chat. Okay, very good. Nigel. Okay, very good. 62 and 27.7 is exactly what I got. Okay. Okay, Keston, I can't see how you got 28.73. Look at that again, please. Okay, so now we have the components of this force. The other force is F2. So F2 is 32 newtons. Okay. So what is F2x and F2y? Now, where is F2 located? It's 48 degrees north of west. So north of west is here. So clearly, before we put anything down, we know that my x component is going to be negative because it's on this side of the in my free body diagram. This is where it is. So this is my F2. So now this is 48 degrees. So x is positive, x is negative, y is positive. So now you can find those values. So what is F2x and what is F2y? And let me see, the angle now is 48. So I'm going to say cosine of 48 and then multiply that by 32. I don't have that written correctly. Hold on. Okay. So for F2, I calculated the x and y components of force 2. Now, remember Newton's second law. It says the net force is ma. So that means that I've got to add up these forces, F1 plus F2. That's my what? My two forces. So because F1 and F2 are forces and they are not even in the same quadrant, they don't even have the same angle, I've got to add this by the component method. So I've got to add all the x components. In other words, I've got to sum up F1x plus F2x. And then F1 y plus F2 y. That's what I have to do. Because remember, I cannot add these. We have learned the importance of the component method. So F1x plus F2x. So that would be 62.1 minus 21.4. Okay, what is that? 62.1 minus 21.4. I got 40.7. So F1x is, in other words, class, what I have now is a new vector where the x component is the sum here, and that's 40.7. So that means that this is 40.7 newtons along the x-axis. On the y-axis, it's also positive. I've got 27.7 plus 23.8, 51.5, and it's positive. So on this axis, I've got 51.5 newtons. Everything is in newtons. So what is summation F? Summation F then, here, I've done this, I've done this. Now I've got to find out what is my net force. This class is my net force, this. And of course, I've got to use Pythagorean theorem to find that value. So that means I have 51.5 squared plus 40.1 squared. I get that. And take the square root. So take the square root of that. And I got 65.27. So this force, my net force, is 65.27. So my acceleration then, is going to be 65.27 divided by the mass. The mass is 16 kilograms. So when I divide the 16, I get 4.07. When I divide that, I get 4.07 meters per second squared. And then I come over here and I find that. Now, in the exam, I may have 4.1 more than one time. So that means that in the exam, you got to find this theta. But of course, we have learned to find theta. Theta is an angle whose tangent I know. Tangent is what? Opposite, which is 51.5, divide adjacent, 40.2, whatever that is, it's close. So now I can find theta. So I say second function tangent, opposite, 51.5, divide adjacent, 40.2. And I get 52.0. 52.0 degrees. Now, it's in the quadrant, which is on my free body diagram, the first quadrant. So clearly, this is north of east. Now, I'm recording this, so I will send this to you because I can guarantee you a problem like this will be on your midterm. A problem like this is on your final. Any questions? Any part of this, before I erase it, any part of this, you can come off mute if you want me to explain anything. Okay. So I went step by step, and I hope you see here the importance of understanding what to do. In other words, in order to add these two vectors, we have to add them using the component method. There's no other way to add them. They're in different quadrants, they have different values, different degrees. There's no other way to add them. And therefore, we have to do it that way. Okay, I'm going to erase this one and go to the next question that you may have. So let's continue to look at the assignment and see if you have any other questions before we move on to the next part of this test, this chapter. Okay, I'm going to clear all this. Okay, so now that we've done that, actually number 11 should be even easier. Does anyone have a question on how to solve number 11? Did you get that answer D, yes or no? And if not, we can do it together. Does anyone need me to do D? I'm going to chat. Just write yes. If one person needs to do it, that's enough for me. Number 11. Did you get D? And if not, do you want me to go over it? Nobody? $11 would be good to go over. Okay, great. So I need to know. Very good. Okay. An apple crate with a weight. So in this problem class, we're given the weight. And the weight is 225 newtons. Pull along, okay, the force is 14.5. So the force is 14.5 newtons. What's the horizontal acceleration? So I need to know horizontal means what is along the what? Along the x. So to find that, I need to know f of x in order to find a sub x. Because x means along the horizontal. So the first thing I do is I find out what is f of x. So f of x we know is going to be f cosine of 19. So I say cosine of 19 times, what is f? 14.5. So 13.7. So f of x is 13.7. I need 3 sig figs. I'm going to go out 4 sig figs. Okay. F of x. Now, according to Newton's second law, we know that F is ma, and therefore A is F over m. But you notice here that we're not given m. Now, I don't know if I went over this or not, but we said the equation for Newton's second law is F equals ma. And weight is W equals mg. Therefore, the mass is the weight divided by g. So that means then I've got to put in the weight, which is given as 225 newtons, and I'm going to divide that by g, 9.8 meters per second squared. And that will give me so many kilograms. So right here, if I was solving this problem in an exam, okay, along the x direction, that's f of x, I I would do one calculation. This is what I would do if I was in an exam. F of x is F cosine of theta. So in my calculator, let me erase this for a minute. Okay, F of the F, oops, hold on. Cosine of theta divide mass. So I would put in my problem, I would say F 14.5 times cosine of 19 newtons divide mass. Mass is weight over G. So I'm going to divide 225 newtons, divide G. And we said whatever goes in the denominator of the denominator, that moves to the numerator. So my G must move to the numerator. So here I'm going to put 9.8 meters per second squared. Now I'm going to solve one problem for my A. 14, okay, start here, cosine of 19 times 14.5 times 9.8 and divide 225. That's what that problem is asking you to do. Okay, let's do that. 14 point, I'm sorry, do the cosine first. We've already solved that problem, but I'm just going to show you how you can do it all in one step. So I got cosine of 19 okay. Then we said times 14.5, get that. Then we said times 9.8, get that. And then we say divide 225, we get that. We get 0.5971. We need 3 sig figs. So we do all that, and we say that A sub x is 0.597 meters per second squared. Okay, that would be answer D. Is that clear? Is that clearer to you now? Is it making more sense to you now, class? I'm going to see if anybody's saying yes or no. Now that I solved that problem, is it making more sense to you? Very good. Only one person? Does that mean that the others is not making sense? Let me know. I'll be happy to do some other examples.
It makes sense.
Okay, great. All right. Now, a problem like this, as you can see, it just requires you to take your time and reason through the problem. You have to be able to reason through the problem in a methodical way. This is almost like a free body diagram shown, because we know that this will represent our x-axis. So I need to know what is the component that's pulling it along the horizontal. But in some cases, you may have to draw the free body diagram. Okay, I'm going to go to the next problem. Okay, now, this problem, I want to see what you can do. So now I want to see you work on this problem, number 12. We've done enough together now for you to, oops. Oh, well, I have this page. Well, no, I don't have this page pulled up. Okay. Okay, number 12. This is the answer, but I don't want just the answer. First of all, I want to know what is the net force? Okay, so we know that in order to find the horizontal acceleration, which we know now is a sub x, I must know what is f sub x. F sub x divided by the mass. So first of all, what is f sub x? What is that first? Somebody give me that number. Okay, I'm going to go over to chat and see who can tell me what is the force along the x-axis. One person has gone over to give me f of x. Let's see what that person is saying, if that's correct or not. Okay. Nigel, that is correct. Okay, Nigel has the correct value for f of x. Anybody else can find f of x? I'm waiting to see if you can do it first, because if you can't do this one, you're going to have difficulty on the ones I've just done. I'm waiting for someone else to give me what is f of x. In other words, class, what is the force along the x-axis? And how do you find that? Look at it carefully. You have to think. Okay. So let's see. Lex and Kaylin and Keston and Kendra and Monier, you all can't tell me what f of x is? Okay. All right. This is what you have for f of x. This is my object. I have this x component, which happens to be 5.9 times the cosine of 43. Do you see that? Because the x component, of course, is the component along the x-axis. But not only do I have that, I also have this force pushing on it. So this force is also pushing on this object. Even though it's pushing from the back, it's still pushing it what? Forward. So I have another force. I have another force on top of that force that's also adding to it. And that force is 3.7 newtons. So that's the force along the x-axis. And when you add that all up, you will get 8.01 newtons. So that is what I'm going to divide the mass by. So when I divide that number by the mass is given, I will get 1.78. 1.78 meters per second squared. So on my calculator, this is what I see, and therefore I choose 1.8. Any questions? Any questions? Okay. I hope you see now what you have to do. You just can't ignore everything we have learned. You see, in this case, you have two forces, and we know that the original Newton's law, we always had the summation. Summation means we have to add up all the forces. In this case, we have what? The first force along the x-axis plus the second force along the x-axis. So therefore, I have to add these up. If I call this one F1, then this one is F2. So I have to have F1, X, and F2, X. That's where the 8.01 came from. Okay, moving right along. Okay, number 13. Two forces act on a hockey puck. For which orientation of the forces will the puck acquire an acceleration with the largest magnitude? So let's just say, for example, we give these numbers some values. Let's give them some values that we know. For example, we know 3 and 4. Okay, let's just do 3 and 4. Oops. Okay, so let's just say we know this is 3 and this is 4. The maximum value that this can have here, we know is 5. Okay, now we also learn that the smaller this angle becomes, okay, the smaller this becomes. In other words, this is the orientation that's going to give us a value that the greatest we can have when they are at this type angle. Anything that's less than that, of course, this is smaller. Then, of course, in C, what we have actually is we have 3 and 4 in the same what? In the same direction. So therefore, this magnitude would be 7. Then here, this means that, say 3 is going this way, which is negative, and 4 is going this way, which is positive. The maximum there can be 1. The magnitude would be 1. And then finally, it says the magnitude of the acceleration will be the same in all 4 cases. And that's definitely not true. So the largest magnitude we know, and now this is true for any problem, the largest magnitude is going to come when they are in the same direction. The same direction. No angle between them, the same direction. That's the largest value we can have. Okay? Let's see. Okay. All those word problems will come back to. Let's see. I think I had a problem down here that I wanted to solve before I leave this section because it's definitely on the exam. Okay, here it is right here. Okay. Now these others I'm going to send to you, and I hope when you study these questions that you can make it make sense to you. In other words, these are action-reaction pairs. This is Newton's third law. And read through it carefully and identify why this is the answer. Why this is the answer. Because the rest of these are just what we call concept questions. And the concept questions are there for you to understand better the conclusion, how they concluded that answer. So the last one I want to solve for you is this one. Okay, number 20. Actually 21. Here, 21. Okay. it says a 70-kilogram astronaut pushes to the left on a spacecraft with force F in gravity-free space. So they're letting us know that we can ignore the force of gravity, gravity-free space, he's saying. So he's not gonna fall down. Okay. So this is the mass of my astronaut, 70 kilograms. The spacecraft has a total mass of, so this is the mass of the spacecraft, and it is 1 times 10 to the 4th kilograms. During the push, the astronaut accelerates to the right with an acceleration of, so they gave us the acceleration of the astronaut, and that is 0.36 meters per second squared. So that means, class, if I know the mass and acceleration of the astronaut, I can find what? The force of the astronaut. So multiply 70 times 0.36. $25.2. So this is 25.2 newtons. Okay, now it says, which one of the following statements concerning this situation is true? I want you to look through this, but the answer is the velocity of the astronaut increases. In other words, it has to increase because he's doing what? Accelerating. Okay, and the others you can tell why those are not the case. But the question I want you to determine is the magnitude of the acceleration of the spacecraft. So the acceleration of the spacecraft is going to be the force on the spacecraft divided by the mass of the spacecraft. So now you may ask, what is the force on the spacecraft? And this is a very problem we had in lecture notes. We said these are action-reaction pairs. So while he's pushing with the force this way, the spacecraft is acting with an equal and opposite force that way. So this force of the astronaut is pushing that way. The force of the force on the spacecraft is pushing that way, but they are equal. So the force on the spacecraft is equal to the force on the astronaut. And because it's asking for the magnitude, I'm not concerned about the sign. Okay? But clearly, this would be negative and this would be positive, but we're not concerned about that. So I have 25.2 newtons divided by 1 times 10 to the 4th kilograms. And I like that it's 1 because that means then that I can just say 25 times 10, positive in the denominator, negative in the numerator, make that negative. A Newton divided by a kilogram is meters per second squared. And then they want me to write this number in scientific notation, which means this number gets smaller by a factor of 10. This number gets larger by a factor of 10. But of course, if it's a negative number, it's larger when the magnitude is smaller. So therefore, I have 2.5 times 10 to the minus 3 meters per second square. Okay? And that's the answer that we choose. We choose answer C. So I am going to send these questions, these answers to you. As soon as we end the lecture, I'm going to send these to you, and I will encourage you to understand the problem, because in the exam, the next exam, we will have a problem like this. I just will have different values. But if you can work this problem, you can work any one that I give you. Okay, so I went a little longer than I had expected on reviewing that, but that's okay. I'd rather take my time and help you to understand the problem in its entirety rather than rushing through. Okay, let us go now to the new share here. I sent this page to you yesterday, and hopefully you have started to fill it out. And I want to do an equation here that I think I did not explain. We'll go over, I think, in today's notes. But the weight, we use lowercase w, and it's equal to mass times g. And weight can be in newtons or pounds. And I think we're going to have that equation in today's notes. I'm not certain if we get to it or not. Okay, so make sure as we go along, you're filling this sheet out, because this is the sheet that I call the comprehensive equation quiz that you can use. Just have it handy to use during the exam. Okay, let me go to, okay, I'm going to now go back to our lecture notes. Okay. Definition of weight. So we said that the weight of an object on or above the earth is the gravitational force that the earth exerts on the object. Now I want to show you the equation that I was trying to show you earlier. So say we have an object on the surface of the earth, just an object. That object is being pulled down toward the center by the force of gravity. And therefore we have an equation that says simply weight is actually the mass of an object times the acceleration due to gravity. And that's why I said weight is just a force. Now, the reason why I prefer to use lowercase w, of course, you don't have to, but I'll tell you why it's a good thing to do, is because in our next chapter, we're going to learn about work. And for work, it's also an uppercase W. So I try to distinguish between work and weight by using a lowercase w for weight. But you don't have to, just a way that I use to distinguish between the two. So what we see here now is that we've already defined weight according to the previous chapter, the previous slide, I mean, as being the gravitational force between the object and the earth. And that's why right here, this is the mass of the earth. So in this object right here, if he's sitting on the Earth's surface, the radius would be the radius of the Earth. And we define that as the weight, which is mg. So that is equal to mg. So that means then, if I want to find the value of g, if I cancel out the m's, the value of g is big G, mass of Earth, the radius of Earth squared. And we can show you that that is exactly what you get. So on the Earth's surface, the value of G, we plug in big G, the mass of Earth, the radius of Earth, we square it. And when we solve all this, class, we get the value of G that we have been using, 9.8 meters per second squared. So that confirms then that little w, which is mg, is also equal to big G, mass of the Earth, mass of the person, divided by the radius of the Earth squared. That's what it means. Okay, so have you ever thought to yourself, how do we know what is the mass or the weight of these distant planets? Well, we're able to solve that because this G is the universal gravitational constant. We can even find the value of G on other planets with the same equation. And some of your assignments tonight will be that. Okay. Now, on the handout that I gave you, let's go to this handout. On this handout, I ask you to define certain terms because sometimes it takes writing these terms out in words, in everyday words that you understand, to get a full understanding of what they mean. Rather than always having an equation, you also can write it in word form. So the words are here for many of these, and you should just be able to copy it in your own words, write it down in your own words so that you understand it clearly. So the first one we have here is normal force. So what is normal force? The normal force is one component of the force that a surface exerts on an object with which it is in contact, namely the component that is perpendicular to the surface. So here I have a block sitting on a table. We've already explained that the weight is the force that's acting downward. And we've already defined that weight. Do I use a lowercase? I use a lowercase w. It's okay. It is mg. And it's always acting downward, never upward, mg. So now we have another notation, and we call that F sub n. And this is one component of the force. So now on my free body diagram, this represents my brick, and this represents the normal force, and this represents the weight. So those are two forces. Now, as you can see by these vector arrows, that these forces are equal and opposite. They're equal and opposite. Therefore, the normal force is simply the weight of this object. That's the only object there. So the normal force, and of course, this is perpendicular because the weight is always perpendicular to the surface that is on. And therefore, we have the normal force. Now, the next picture. Again, this force now, this normal force, is actually greater than the weight of the block. And that's because there is an additional force pressing down. So not only do I have the normal force here, I have the weight here. And I add these two together and I get the normal force. So now I have an equation. You see, the normal force is always acting upward, and it is equal to all the forces that's acting against it. Or in this case, all the forces that's acting with it. So now look at this. This is the importance of having an idea of the free body diagram. Because on my free body diagram here, this is my normal force, F sub n. This is my weight, 15. And this is also acting downward. And this is 11. You see, on my free body diagram, both of those are acting downward. So therefore, my normal force will be the sum of these two. Then here, okay, I have a force that's acting downward. That's the weight. But I have a force that's acting upward that I'm applying. That's 11 newtons. So what's my normal force? Well, my normal force now is going to be the difference in these two forces. So clearly my normal force now, okay, here, the difference is what? This, which is acting downward, minus this, which is acting upward. And then that will give me 15 minus 11. So my normal force now is just 4 newtons. That's my normal force. Now, I want to go ahead and introduce this to you because I have found that if I introduce this to you now, it's actually easier than later. So let me go back to this picture. I want to introduce this to you. You see, in this picture, this is my free body diagram. This is my object. But what happens if my object is sitting on a surface like this? Okay. Now, you say, what does that mean? That means that this object now, I've got to be able to distinguish it from one that's sitting on a normal surface like that. So what I want to show you now is another way to do that. So this looks confusing. I'm going to show you another way to look at that. Let's see, I don't know how to get this off. Let me see. Let me go out and come back in again because it's not going to work. Hold on. Okay. So in my free body diagram, this is my object. And we said that the normal force is always perpendicular to the surface. So this is my surface. So In other words, let's just draw it like this. This is my block. This is my table right here. Okay, perpendicular. Now, if I take that same block, but my table now is oriented like this, and this is my block right here. So we said that this weight always acts downward. But the normal force is one component of the force that a surface exerts on an object with which it is in contact, the component that is perpendicular to the surface. So this, of course, is my weight, the way it has always been. But class, this is my normal force. You see? Because it says the component that is perpendicular to the surface. So that means that my normal force is acting perpendicular to this surface. So in this case, my weight is no longer going to be equal to my normal force. So let's just do one we know. Let's just say my weight is 10 pounds, okay? 10 pounds. Now, here, this is the hypotenuse of my new triangle. My new triangle has a leg like this and a leg like this, perpendicular. Now, it would take some time for me to go through the derivation of this, but if I had to move this along, take this table and align it along some angle, okay, whatever that angle is that I move this table up from its parallel, when it was parallel right here, okay, I moved it up so much theta. So that means that this represents theta. So now, because we have learned the right triangle, this side, this is the adjacent side, this is mg cosine of theta. I say mg because the weight is 10 pounds, which is mg. Okay? But for right now, I'm just saying it's 10. I'm not going to use a unit. Just say 10. 10, just 10, okay? Now, this is mg, which is the weight, sine of theta. So that means then, in this picture, my normal force is 10. In this picture, my normal force is 10 times the cosine of theta. Now, this part, mg sine theta, is actually, if I were to lift it so much, it would be the portion of the force that would make it slide back down the table if it overcomes friction. I'm going to show you that now before I get to the frictional forces so you can see what that means. So is that clear to everybody? In other words, I have my surface here, but I have oriented it so that now it's at an angle, theta. So my object that was sitting here with the weight coming straight down is now sitting here, but the weight still must come straight down. But in this case, my normal force is here. In this case, my normal force is here. That's what I want to explain to you. Okay, y'all got that? keep this slide so you can have it for future reference. You're going to need it, believe me. And this is the best picture that the author gives for me to explain it. Okay. Now, what is apparent weight? That's another word I think you have to define. So let's understand what it means first. The apparent weight of an object is the reading of the scale. It is equal to the normal force the man exerts on the scale. So here, no acceleration, or he's moving at constant velocity. And that means then that his real weight, how much he actually weighs, is equal to the reading on the scale. Now, what happens when an object is accelerating upward? You see what happens? If it's accelerating and it's upward, his apparent weight appears to be more than his true weight. You see, what he's made of, his mass times g, that gives him his true weight. But this is his apparent weight. So what you understand from this is one simple thing to understand. When the object is accelerating upward, it appears to gain weight. It appears to have more weight, as opposed to when it is accelerating downward. The object is moving downward. Say in an elevator, you're moving downward. The apparent weight appears to be less. So up is more, down is less. Then free fall. Free fall means that he is moving at the same acceleration as the free fall value for g, which is 9.8 meters per second squared. And when he's accelerating in free fall, it appears that he has no weight. So the only way that he can have no weight or appear weightless is that he is moving at the acceleration, with the value equal to g. That's called free fall. Okay. So what is my equation for my normal force? My normal force is the sum of all the forces in the y-axis, or whatever we're going to call the y-axis, in this case, the vertical axis. So the normal force, in this case, it is the weight minus the weight, which is mg, okay? And Newton's second law says that sum of all those forces must equal to ma. So all the forces in y are the normal force minus mg, because normal force is up, mg is down. And Newton's second law says that must equal ma. So when I solve for the normal force from here, the normal force then is mg plus ma. So the normal force, which is in this case the apparent weight, is the true weight plus mass times acceleration. If it's not accelerating, it's just what? The normal force is its true weight. But in the case when it is accelerating upward or downward, we see that it is can be more if it's upward and less if it's downward. And then when this g is equal to the value of free fall acceleration, then we're going to get what? 0. Because this is going to be negative 9.8 plus the g, which is always magnitude. This number here, class, is always magnitude. The weight is always magnitude. Okay. The second type of force we're going to discuss very quickly are the static frictional forces. Now, so we've already talked about one contact force, the normal force. Now we have other forces called frictional forces, static when it's at rest, kinetic when it's moving. The component of this force that is parallel to the surface is called the frictional force. So we have frictional forces. So that means this is why this free body diagram is going to be so important, because on the free body diagram, you must label all the forces. If the object is in contact, the first force you know it has is weight. The next force you know it has is normal force. Another force it's going to have now is this opposing force. The frictional force is always an opposing force. And you know that when you get ready to push an object that's on a surface, the reason why it's difficult to push it is because you must overcome all these forces in order for it to begin its motion. So the next equations I have for you, well, let's go over this part first. So what's happening? When the two surfaces are not sliding across one another, this is called static. So we use the term F sub S. Now you notice this arrow and this arrow are equal because according to Newton's third law, these must be equal and opposite. The harder I'm pulling here, the more force is resisting. And you say, how can that be? It's the law of nature. And you can prove it because what happens is once you get beyond this force where there is no movement, you have overcome whatever this frictional opposing force is, and the object just begins to move. But as long as it's at rest, this value, the pulling force and opposing force, are equal. So therefore, my first equation says that the magnitude of the static frictional force can have any value from 0 up to a maximum value. In other words, it can begin at 0 and have any value up to a maximum value of this equation, F of S max. And that is mu sub S F of N, where this mu sub S is called the coefficient of static friction. It's just a number that I'm multiplying by the normal force. It's just a number, no units, just a number. And it's called the coefficient. And I'll show you a chart in just a minute. Here's my chart right here. You see, scientists and chemists and engineers, they've already studied these materials when they are in contact. Glass on glass, ice on ice, rubber on dry concrete, rubber on wet concrete. And they are showing you the values of these coefficient of friction. Mu sub S means it's at rest. Mu sub K means it's moving. Okay, we say kinetic means it's in motion. So my first equation then is this. The next equation, well, let's talk about this first. Now, the magnitude of the frictional force does not depend on the contact area. And that's because this normal force, F of N, weight, F of N, is the same here, okay, and the same where? Here. The orientation, what? Doesn't matter because it's dependent on the weight, and the weight remains constant even with the different orientations, what's on this surface or this surface or this surface. And that's kind of difficult to think about because of the fact that we're thinking, well, I have much less contact here than I have where? Here. But the magnitude of the frictional forces does not depend on the contact area of the surfaces. It depends on the weight of the object. Okay. The next equation is kinetic. So we said static frictional forces oppose the impending relative motion. In other words, the objects remain at rest until they reach a value where it begins to move. Once it begins to move, we say it's kinetic friction, which opposes the relative sliding motion that actually does occur. So now we have another equation, mu sub k f of n. So now we're going to stop on this slide here. I want you to study this example. The author had an error in one of these. I can't remember which one it was. Okay, the tension force. Let me go to here. Okay, so notice now that I have normal force, coefficient of static friction, static and kinetic frictional forces, the tension force. So I'm almost done. Okay, so I would like for you to come here and write. I would like for you to come here and fill these in. Okay, so for frictional, go ahead. Someone had a question? So here, frictional force, static, we call that F sub S, subscript S. And we said that that is mu sub S F of N. Then here, kinetic, that is F sub K, mu sub S F of N. Now, of course, we said that this is the force where the maximum it can get just before it starts to move. Now, what are the conditions for equilibrium? The conditions for equilibrium is all the forces in X must be 0, and all the forces in Y must be 0. That is called equilibrium. All the forces in X, we'll discuss that in the next problem. So now I'm going to give you just a few problems to work on to bring you up to speed on what we have gone over. And then I'll be able to go over the more of the problems in the next lecture, 247. Okay, please keep up with what we have. Save this in on your desktop, on your computer, on your phone. Save all these notes. If I were you, I would go ahead and review them right away and then use them to work on this assignment. So I'll be sending you an assignment, some problems from chapter 4 that require you to work on weight, to work on gravitational force, apparent weight, frictional force, and equilibrium. Those are problems coming up next. Okay, do we have anything I need to go over before we end the lecture? Anything that I've gone over that I need to review before I say we're dismissed? So if you don't have anything you want to go over, you can go ahead and sign out for today. And if you do, you can stick around and ask questions. Otherwise, you can sign out your name for today's lecture if you're ready to go. I know we covered a lot, and I'm going to send these problems. Just work on them the best you can. If you have difficulty, that's okay. You have to just try. You have to just try on your own, and then we'll go over it again together in the class. Okay, so Nigel, are you signing out?
Yes, I have a question, but I may just call you later.
Okay.
Yeah, I got a meeting I have to attend soon.
Okay. I was trying to get through before 3. I know you said you go to 3, but I was trying to get through as close as I could to the regular time.
Yeah, I appreciate it.
Okay.
All right, bye-bye.
Bye-bye. Guess it's not out already? Oh, I see now. Okay. There's 2 more people still there. Okay, 1 more person still there.